Okay, perfect. So we are online. And I guess that we could start perhaps, Ron. I was thinking that if you could tell us a little bit about how you went from taking logic lectures with Herbert Enderton, no, to doing a PhD in finite model theory with Robert Vaught, and how did that happen? How did you pick that problem? What
Sure,
did you?
wonderful. Thank you for asking. So first of all, how did I get into logic in the first place? Well, when I was an undergraduate at Dartmouth College, one of the requirements was philosophy. I thought, ugh. But hey, if you took a course in mathematical logic, that counted. I thought, great, I can eliminate having to take some nasty course in philosophy by taking a math course. So I took a course in logic, and it was taught by Donald Kreider, who was truly a magician in the classroom. He was fabulous, and he really turned me on to logic. I thought, wow, this is really good stuff. And in fact, the next year, he was teaching a course in recursive function theory. And I thought, I have no clue what a recursive function is, but if Kreider's teaching it, I'm going to take it. I took it, and it was a great course. So then I went off to Berkeley, and I intended actually to do a thesis probably in probability theory. That's what my senior thesis at Dartmouth was about. But now at Berkeley, they had various rules. And one rule was your oral exam has to be analysis and algebra and one of the following: logic or differential equations or geometry. And I thought, I'll take logic. So the only reason I studied logic at Berkeley was because, that was going to be the topic of one of my oral exams. So, and the person who taught my course, Introductory Logic, was Enderton, who wrote the book also. And he was also a fabulous teacher, but he introduced the problem that really got me excited. It really, really, really got me excited. And that was Osser's problem. And it's the following. Let's define the spectrum of a first order sentence. It's the set of cardinalities of its finite models. So for example, if sigma is the conjunction of the field axioms, then the spectrum of sigma is a set of powers of primes. So Osser's problem is the complement of every spectrum a spectrum? And I thought, wow, what a great problem. So I started working on that problem. And of course, I didn't solve it. No one solved it. It's still open to this day. But here's how it led to my thesis. So I realized, well, a spectrum, like in the case of the conjunction of the field axioms, you could view it as an existential second order sentence. There exists a plus and there exists a times such that there's a conjunction of the field axioms hold. And I told that to Vaught, my advisor, and he said, well, instead of just having a sentence, there exists Q sigma of Q, why not run have there exists Q sigma PQ, where P is not quantified? That's existential second order logic. I thought, wonderful. And in fact, I tried to give him credit for that in my paper I wrote on finite model theory. From my personal perspective, I gave him credit. He said, no, take it out. No. That's what thesis advisors do. You can't give me credit. So I thought, okay. But now I had existential second order logic. And I thought, oh, great, existential second order logic. And I realized, well, first of all, I realized it was an NP, and the problems like three colorability. I could see I could do it. And so then I was able to show exactly it's NP. So that's how I got into what's now called Fagin's theorem. But let me tell you something else. How to get into the 0-1 law? It was also, believe it or not, from Osser's problem. How is that? Well, I'm trying to take the sense of the conjunction of the field axioms, and we want to decide if its complement is a spectrum. Well, the very, very, very naive thing to do, in fact, I mentioned advice says, come on, is take the negation. So write the sentence not sigma, where sigma is a conjunction of the field axis. And of course, I know that's not going to give the complement, but I thought maybe I can get something interesting. So I thought, gosh, in this case, not sigma is really uninteresting. I mean, it's so easy to be not a field. I mean, so many things could go wrong. So I thought, sigma is interesting, not sigma is very uninteresting. And I thought, is this a theorem? Is it the case that if sigma is interesting, then not sigma is very uninteresting? I thought, how do I make not interesting precise? I thought, probability one, that not interesting means that you take the fraction of structures that satisfy it, take the limit as n goes to infinity, there's one. So then I thought, is there for every sentence is either sigma or not sigma have asymptotic probability one, and that's how I got into the 0-1 law. So that's how I started thinking about it, and how I eventually proved it. So that's my history where Osser's problem, which is still open, led to a lot of stuff for me.
But and at what point did you come across the work by Geifman that you used?
Oh, that actually, you're really on top of it. You do your homework. Actually, Vaught told me to go look at Geifman. You're absolutely right. So I went to see. So I told Vaught what I was doing. He said, "Go look at Geifman's paper." I think I wrote this down. And Geifman actually had we now call the what do they call it? The what kind of sentences? What's the word?
With a random structure.
No, but not random structure, but the
extension axioms.
Extension axioms, exactly. So Geifman, but he's using a totally different context. He's using it with infinite structures. So I thought that's just what I need. Those axioms are exactly what I need. And in fact, Vaught told me, call up Geifman and tell him about your 0-1 law and how you use extension axioms. So I called up Geifman on the phone. I was a lonely graduate. He was this big famous person. So I sort of nervously told him. He said, uh-huh. I said, now I got the following theorem. Uh-huh. I thought, oh man, he doesn't like this at all. I was very disappointed. He had no interest whatsoever in 0-1 law, even though I use extension axioms. So thank you. You're also great to have in the audience, Jeremy. You asked, what you've done is you've done your homework. You've read my various papers, and you know the things I mentioned in the paper. So thank you.
I have a few more questions about that.
Go for it.
The big irony, you went into logic trying to escape philosophy, but you know what Geifman does today? He's a professor of philosophy. That's exactly.
Is that right? Is that right? I did not know that.
At Columbia University.
Have you interacted with Geifman?
Yeah.
Is he a nice guy or just not nice to me?
He's an awfully nice person. He's extremely nice person.
Yeah. Oh, okay. So maybe he was not amused that he didn't come up with 0-1 on. Who knows? He just didn't see.
I don't know. I have no knowledge of that.
I see. Okay, great. Thank you. By the way, I see everyone else's picture on the screen, but not mine. Is my picture shown on the screen when I'm talking? I don't see it. Okay, good, because I don't see it. I just see a tiny little thing. I see Phokion right now because he was the last one to speak. I just didn't know if something is masking me from going onto the screen, but I am there, right?
You are there with headsets and a white beard, yes.
Thank you. Well, hey, Phokion, who's talking about white beards here? And white hair?
Sorry, Ron, yeah?
Oh, I'm done.
Okay.
Yeah, I was just saying.
I want to tell you something about Ron. The concept of the Fagin number. Do you know the Fagin number? You don't know the Fagin number. Okay.
No.
Okay. So the Fagin number is a number that has the opposite properties of Erdős number. The bigger, the better. And the history of this is the following. In 1990, Ron was invited to give a talk at the ICDT, the International Conference on Database Theory. And this was the heydays of finite model theory. And he gave the talk, Finite Model Theory, a Personal Perspective. And he wrote a paper. The talk was very successful. So he kept giving the talk. And I think he still gives the talk.
Actually, I had it recently because you shamed me for Cannon saying you got to update it, Ron, and tell all the recent stuff.
That's right.
So
that's right.
You shamed me out of it.
So I have listened to the talk more than a dozen times. So
really?
I developed the concept of Fagin's number, which is the number of times you have listened to the talk.
So it shows that it's a measure of loyalty. The Fagin number is the number of times you heard the same talk by Ron.
The same talk. Now you have this other talk. Now he's giving the other talk, this theory and practice, which I have also heard 5 or 6 times. I mean, so you can choose. I don't know how to add these two together, but that's the Fagin number. That's the Fagin number.
I love it. Okay. So everyone in the audience today has Fagin number at least one, and so
yes, exactly.
Your number can grow. How about you guys?
Yes.
I guess.
We're talking about the same.
I have seen the talk 2 times. Yeah, I saw it in the IBM event as well.
This talk. I didn't have real value logic in it at the time. It was just 2 parts, right? When you heard it.
No, that's true. At the time, it didn't have. Well, it had a little bit of the real value logic. You were just starting that. And then you gave the one with the real value logic in the second event that you guys organized not so long ago. Maybe I don't remember what when it was, but I think it was easier, no? Like, but it was only a 30 minutes one.
Yeah.
It was very much.
Oh, I
condensed.
don't think I'd have time to do that in 30 minutes because I can't even get the first two parts done in 30 minutes.
Yeah, no. In the 30 minutes one, you only gave the real value logic part.
Oh, just real value logic. Oh, I've given
Yeah.
talks to real value logic. That's true. I have done that.
But
Now, I don't know if
actually,
that counts. Does that count for Keon? If he attended a talk I gave on real value logic and attended this talk, which has real value logic as a piece.
I don't know. You can decide, Ron. But I think you should give the personal perspective again.
I have another question. I guess, I mean, related again, because I mean, you were working with both, Ron, and I wonder because Phokion mentioned earlier during the conference, no, that there was this paper by William Tay that he indeed was sort of refuting, no, the preservation theorem for substructures in the context of finite models. So I wonder, Phokion, do you want to say a little bit about that story? And I wonder whether Bod would have had any knowledge of this.
He never mentioned it to me. So even though I was doing finite models, he never mentioned that theorem to me ever. So anyway, go ahead, Phokion. I'm sorry.
So you want me to repeat what I said earlier? Is that what?
Yeah, basically, yeah, because I think this is an interesting.
Okay, so Dana Scott and Patrick Supis wrote sometime around 1956, 1957, a paper on the theory of measurement. They were trying to formalize what it means to do measurements in science. And they brought in a first order logic into the picture. I don't want to go to the details. And they were aware that basically they're dealing with finite models. So towards the end of the paper, and almost out of the blue, they raised the question of whether or not what we call now the Wostarsky theorem, which is preservation under substructures, if we have an FO preserved under substructures, is equivalent to a universal first order, whether or not this holds in the finite. And the paper was circulated, and Bill Tate, who was quite young at the time, got hold of the paper, and he did not believe that this conjecture would be true, and he came up with a counterexample. The two papers were published, I think, in the same year, 1958, in the Journal of Symbolic Logic, if I have it correctly. Certainly Tate was in the Journal of Symbolic Logic. In some sense, in terms of a pure finite model theory result, this is really the first result that I know in finite model theory. The paper got forgotten. In the 80s, Yuri told us in the morning that after the talk of Moshe Vardi, went home and started thinking about classical results of model theory in the finite. He came up, he and Saharam Shelah came up with the failure of the Wostarsky theorem in the finite, which is essentially the same construction as Bill Tate's. Now, of course, we know the history, so Tate gets the credit, but for a while, it was part of the discovery of failure of classical finite model theorems in the finite. I mean,
Let me do this. Forget a trivial. Oh, I'm sorry. Go ahead.
No, I finished. Yeah.
Okay, a trivial example is compactness that everyone knows immediately. You know that compactness fails in the finite case. Where you say there exists at least one, there exists only two, there exists only three, so there's 4 points. Every finite subset is a model, but the whole thing doesn't. So someone must have talked about compactness fails in the finite case, but maybe they never wrote it down. I don't know.
Well, that's obvious. The compactness is obvious. Okay, the compactness is obvious. I mean, it's nothing. On the other hand, you have to think a little bit why Craig interpolation fails.
That's true.
And you have to think a little bit why Beff definability fails. And these are also not difficult. But the preservation under substructures is a very clever counterexample that Tate. And I asked him how he came up with this. He said, "Oh, I thought it was a silly conjecture," and he sat down and disproved it. The other thing that's interesting here is that formalizing theory of measurement, in some sense, is also part of the motivation of the first proof of the 0-1 law, the proof by Glebsky, Kogan, Jogonki, and Talanov that Yuri mentioned again, I did not know that Kogan, Yogon, and Talanov were the students of Glebsky, but Yuri claimed that they were his students. That's very interesting. They were interested also from calculations for measurements. And the proof, if you look at the proof carefully, it's a quantitative version of elimination of quantifiers. You do quantifier of eliminations and you calculate probabilities at the same time. So it's a very different proof and very interesting proof.
I remember at first, Phokion, we didn't understand that Yuri pointed out that it existed. And I shared the paper with you, and you and I and maybe Moshe looked at it. We did not understand the proof at first, until we struggled a while.
No, but I have written notes way back when I was visiting IBM in 86, 87 with the full details at the time.
Yeah, but didn't we struggle at first? I recall that we struggled.
The paper is very dense, but I think eventually once you think of it as an elimination of quantifiers, then you write down the proof. Yeah.
Gotcha.
It is very interesting. And in fact, yeah, I'm kind of curious. So how come, for example, Ron has mentioned before in conversation that Vaught was sort of like looking at him and saying, oh, you must have had a lot of fun doing this sort of finite model theory.
Oh, he did. Boy, you know everything, right?
Well, I mean, I don't remember. You have told me. That's how I know.
Right. Oh, yeah. But I mean, Vaught told me, he envied me. He said, you seem to be having so much fun doing this work.
But it's kind of curious that no one had tried to do this systematically before, no? Like, and for example, Bill Tate, when you talked to him, Phokion, so was he aware that this had been rediscovered in some context? Or,
no, he was. I don't know that he was. I don't think he was aware. Bill Tate was a proof theorist and a philosopher, so this is something that he did on the side one time, and he thought it was over. I mean.
Right. Okay. So there was
no systematic effort for the development of finite model theory until really after Ron's thesis in the 80s.
And what was the point? Because Ron has also told us that. So Ron, you have mentioned that you were a little bit disappointed at the beginning, no? That people were not citing the paper.
Absolutely, it's true. The funny thing was, I owe a big debt to Neil Immerman. So I write my thesis, and I had like 5 papers come. I had 5 papers come out of it, and no one seemed to cite it. No one seemed to care. I thought, bummer. You know, I think this is cool stuff, and no one cited. Then Neil Immerman somehow came along, and he cited the paper with that we call now Fagin's theorem, and suddenly I got zillions of citations. I mean, so the door was opened from nobody caring about it to suddenly lots of people caring. And I give Neil credit for just somehow introducing it to the world and calling it Fagin's theorem.
Wow, interesting. And Phokion, in your case, so how did you come to the topic? How did you end up doing finite model theory?
I started from the infinite and went down to the finite.
That's what I mean.
I think that's the best way to put it. I had worked at UCLA with Yannis Moskovakis on generalized recursion theory, which was a very popular topic in the 70s, and then died sudden or natural death, depending on your perspective, just about the time I was finishing my thesis. And so I had no idea. Finite models were trivial, of course, right? That's what we all thought at the time. But then I learned about NP, and Steve Homer, who's a student of Gerald Sachs, I was at Chicago as a postdoc. He mentioned, this is 1979, he mentioned the P equal NP problem, and somehow he knew of Ron's theorem. And I said, oh, you should be able now to separate NP from co-NP, because we know how to separate the existential second order from universal second order. We diagonalize. And of course, none of these work. And then you start digging deeper, and then you realize that the games may be relevant here. So we tried for a while the games. But then I was lucky, I got into this through 0-1 laws. I heard a talk by Cameron, who's a algebraist at UCLA, about 0-1 laws, and I got very excited about 0-1 laws. And so that was the transition for me, the combination of learning about NP Fagin's theorem and learning about 0-1 law through Cameron's talks. And already in the 80s, there was significant activity around 0-1 laws. There was, I mentioned the work of Jim Lynch, where he looked at what happens when you have function symbols, and he saw the convergence law. There was very beautiful work by Kevin Compton in his thesis at Wisconsin under Kistler, who looked at 0-1 laws on restricted classes. And he connected 0-1 laws to the behavior of the exponential series of structures. It's very beautiful work that gave us a lot of insights. And then together with other people, we have started working on 0-1 laws on restricted classes that were not covered by Kevin Compton's results. So I think a comment I would like to make in what Ron said about Neil Limmerman should get the credit of realizing that the Fagin's theorem is not an isolated result, but it's part of a bigger picture, which you can call descriptive complexity, that you can match definability in logic with complexity classes. And you can do this, of course, in some cases you don't need the order, in some cases you need the order, and then we're going back to the logic for p time. So all these ideas came around about that time.
And of course, the Immer-Mavardi theorem.
Yes, the Immer-Mavardi, that's exactly part of this picture. That's exactly part of this picture. So these were, in some sense, it was low-hanging fruit, and it was discovered around the same time. That's how science progressed. People look at isolated results, then they see there may be a bigger picture, and then you go on and develop it.
I have to tell you another funny story about Vought, since we're talking about Vought, and that's the following. So I had an NSF fellowship at Berkeley, and after 5 years, and I love Berkeley, and after 5 years at Berkeley, it was going to expire. I think I may have had a world record for NSF support. I may be wrong, maybe you can tell me. But anyway, whatever it was, I was going to have to leave. So I was going to be only 6 years at Berkeley altogether, which was a lot. But anyway, I just didn't want to leave Berkeley. I was having so much fun, and I loved both the work and the campus and the people and everything. So I went to see Vought, and I said, well, I guess I'm going to have to leave at some point because my NSF fellowship is running out. He said, Ron, I would have given you your PhD thesis last year if you had just asked me. I would have given you your PhD last year. So anyway, I thought it was an amusing story that he never bothered to tell me when I was done. He said, as long as I keep going, why stop him?
So he was a perfectionist, Robert Vought.
He loved it. And we had fun. I always enjoyed talking to him. And so anyway.
Well, also there was a tradition that Tarski kept his students for a very long time.
Oh, I didn't know that. Is that true?
Pfefferman and Chang stayed there for a very, very long time.
More than my 6 years, huh?
More than your 6 years, yes.
Wow. Holy cow.
Another quick question, I suppose, that comes to mind because of what Phokion was saying before. One thing that Ron is always very amused, Phokion, is the fact that there is a way to prove, of course, the 0-1 law without using compactness, not by the original.
With games, I love that.
So this argument with Eren Freud, games, this is due originally to you and Moshe Vardi? Is that from the paper?
I don't know where that came from. I don't think I invented it. I'm pretty sure I heard it from somebody, but I may be wrong. Do you know I'm talking about Phokion, the proof of the 0-1 law using?
Ron, I thought it was Phokion and Vardi that
it could be.
So with Moshe, we wrote this paper, Infinitary Logic and 0-1 Laws, where we showed the 0-1 law for finite variable infinitary logic, right? And we gave different proofs there, and one of them is with games.
I see.
One of them is with games. So in that sense, it implies the 0-1 law for first order. I had not seen a proof before of that type, but our goal was to see the limit of 0-1 laws because we had the 0-1 law for first order, then there was the Blas-Jurevich-Kozen for least fixed point logic. Then Moshe and I had a result in 1987 for partial fixed point logic, which is an extension of least fixed point logic. So we wanted to understand what is the limit when you put recursion mechanisms. And all these logics are subsumed by L omega infinity omega, and that's the limit of 0-1 laws when you take the infinitary logic approach, because even cardinality is described by in L omega 1 omega, but you need infinitely many variables. Okay, so in some sense, the finite variable infinitary logics delineate the boundary for what logics you can have the 0-1 law under the uniform measure. Okay, when you put other measures, the story changes, it's more complicated.
Interesting. And by the way, so another little quick question, maybe one of you can answer it, because in Ron's original paper, he tells the story how Rolando Schwacke mentioned to him that in fact there was a 0-1 law in Carnap's work for monadic predicate logic. Do you know by any chance what is the exact reference for this? Because it's a little bit difficult to find.
I didn't cite it in my paper, no.
Yeah,
I did mention the paper about Carnap.
That's a very big book. The one that you mentioned is a very big book.
Oh, it's a big book? Oh, okay. And I remember, yeah, I cited there that Carnap improves 0-1 law when you have only unary predicates.
Yeah.
But the citation I gave was a big book, huh?
Yeah.
Oops, sorry about that.
Big book by Carnap. So I guess at this point, does anyone want to ask a question or make some intervention?
This is fun. I'm enjoying this.
And I mean, it's fantastic that you guys are willing to chat about it.
Oh, it's so much fun.
Yeah, it has been very interesting. Thank you so much for sharing the reminiscence.
Okay. And I feel like people should not be shy. If you have something that you might want to ask, please feel free to do it. I really wanted this to be sort of an informal conversation more than anything. So actually,
I would like to make a comment, Guillermo.
Please, Javier, please go ahead. Yeah.
Yeah, a comment related to this discussion about the start of the actual finite model theory that had been explained by Professor Kolaitis very clearly. But I want to point out that there is a very special year, which was 1982, because in that year, maybe Professor Kolaitis was there was an ACM symposia on the theory of computation. And in that symposia, there is a paper by Immermann where he presents the descriptive, he started the descriptive complexity theory with his result about capturing polynomial time. It's in that symposia in 1982, and it appears in the proceedings of the symposia. In that same symposia, there is a paper by Moshe Bardi.
Yeah.
That Phokion mentioned before.
Yes.
And in the same year, there is a paper by James Lynch, which with the title Complexity Classes and the Theory of Finite Models. This is the first time that I saw that term, the theory of finite models, in a paper. And I believe there is a fourth paper in that year. A very famous paper in the community of databases, which is the paper by Chandra and Herod called Structure and Complexity of Relational Queries.
Mm-hmm.
I believe those four papers are the founding papers of what we call nowadays finite model theory, not in relation with the 0-1 laws, which of course appear much earlier with Professor Fagin. And well, this was my comment.
Yeah, well, again, thank you for this observation. Yes, 1982 was a very good year. This is the Stock conference. The Immermann-Vardy theorem appeared independently by Immermann and Vardy. These were different papers. The Chandra-Harel paper, I think, was a little earlier. They started in 1980. But the descriptive complexity really also is part of Ron's thesis. And even before that, there was the work by Johnson and Selman, who characterized spectra. They basically saw that spectra are the problems that are in non-deterministic exponential time. So the question of whether the complement of a spectrum is a spectrum is the complementation problem for next time. When you put the relations, then you drop down in NP, and then you have Fagin's theorem. What is interesting, perhaps, in what Javier is saying, is that there are these two different motivations. One is to connect logic and complexity. The other was coming from databases. Because the Vardy's paper and the Chandra and Harel paper were papers in databases.
That is right. Yes.
So there was a confluence. There was a confluence of these things that came together.
Well, you mentioned a slight controversy about the word descriptive complexity. So Wade originally came up, and maybe it was Hartmanus, I don't know, but it suggested the term descriptive complexity, describe how hard is it to describe a problem, i.e. what logic is needed, and in contrast to computational complexity, which is hard to compute. So that's the way I view descriptive complexity. It's how hard it is to describe, computational complexity, how hard to compute. But now many people take descriptive complexity to mean the connection between how hard to describe, what logic to describe, and how hard to compute. So how do you guys feel about it? I mean, to me, descriptive complexity, I like the original notion. How hard is it to describe? What do you think? Any thoughts on that?
I didn't even know that the hard to describe is the original. The motivation really is from descriptive set theory.
Yeah,
the term was used there in the beginning of the 20th century. Where you study the definable sets of reals or the definable sets in metric spaces. And you try to, it's what definability is all about. What are the properties of definable objects? What does the syntax tell us about the structural properties?
Right.
So NP, your theorem, Ron, is not how hard it is, but it's connecting.
It's connecting. Yeah, but that's what I view. I view as connection between descriptive and computational complexity, whereas some people view that as descriptive complexity, period. To me, descriptive complexity is, as originally defined by Hartmanus or whoever it was, is how hard is it to describe a problem? How, in other words, what logic does it take to describe it?
Yeah, perhaps it's interesting to notice that after this date in 1982, there was a very interesting phenomena. I was working in abstract model theory. I was very much interested in that, and there were very few people in model theory working on that, but great people like Yuri Gurevich, like Sharon, like Chela, like Van Anen. And at some moment, I was in communication with some of them, Janusz Makowski, and at some moment I felt alone. I felt the strange feeling that I was alone because all these people were rushing to finite model theory. They start doing finite model theory and abandon, in some sense, the actual infinitary abstract model theory. That was a very interesting phenomenon, I would say.
One more comment about 1982. There is another very important paper that came out this year, but in a different conference, and this is Geifmann's locality paper. That was 1982 in the Logic Colloquium. So totally different conference, totally different motivation. But again, it's a very influential paper in finite model theory.
Yeah, I think so.
And here there is a question. So was Geifmann ever thinking of himself working in finite model theory? Phokion, maybe like when you met him, did you ever ask him something like that?
No, I have not asked him. I interacted with him. I spent a year at Stanford in 1987, 1988, and he was there. We are both part of von Pratt's team, who was trying to develop semantics for concurrency. So we overlapped there. And that's how I know him from that time. I have very fond memories of his kindness and, of course, his brilliance. I did not ask him this question, though.
Well, has he written papers, Phokion, that talk about finite model theory?
Well, this is the paper of locality.
Oh, that paper, I see. Okay, got it.
And he has written a paper with Moshe Vardi, where they use the compactness theorem to prove that connectivity is not definable in first order logic on finite structures. Because we say, oh, you can't use compactness. Well, they say you can use compactness. In some sense, what they do, they're doing the ultra product construction, which works on finite and infinite. That's what they do.
My proof in 0-1 all used compactness. And I was very proud of the fact that I had a theorem in finite model theory that used the compactness theorem as part of the proof. I was very proud of that. So
that was interesting indeed in that original paper.
right.
But I mean, I guess that for the proof of that of the 0-1 law, I guess that of course the methods that Phokion and Moshe Vardi would have had to develop obviously could not rely on compactness because that was for an infinitary context, and then that would not work. But I think it's very cute, no, that the original proof did use compactness in some non-trivial manner. Yeah, it's indeed very interesting. So are there any more questions, comments?
Well, I want to say that when I was a graduate student, those were times where you could read and almost understand most of the papers in the Journal of Symbolic Logic every time it appeared. Now it's almost impossible. But when I saw, I have to say that when I read Professor Fagin paper about the 0-1 law, I was fascinated. For me, I have to say that's a gem. That's a jewel of mathematical logic.
Well,
at that moment, it still is, I think, one of the most beautiful results in mathematical logic. Yeah.
Well, thank you. By the way, if you don't like what's in Journal of Symbolic Logic, I think you should complain to the president of the Association for Symbolic Logic. Give him a direct complaint if you can find him. By the way, that's for those who don't know, that's Phokion.
No, but I think that Phokion is a very reasonable and nice president of the ASL. I think we are very fortunate to have him.
Well, the field has advanced. That's all that's going on. The field has advanced. The age of innocence is gone.
The age of innocence. Okay, so are there any more comments, questions, remarks?
This has been a lot of fun. Thank you for setting up this session. This has really been fun.
And thank you, Ron, for being here, and Phokion and Javier and everyone. It's been very lovely indeed. And I think that
Thank you.
It's been a pleasure. Thank you for organizing.
Really?
But now it's 11 o'clock
now
here.
it's time to exactly. Now it's time to. It's a good moment to end.
Yes, yes.
Thank you very much.
Okay, thank you, everybody. Bye.
Goodbye to all, and thank you.
Bye.